Electricity is a curious phenomenon. It's been understood for well over 100 years, and yet there's still something vaguely mysterious about it. And you know, the really curious thing is, there's no direct electrical connection between appliances like your video machine and the power station. It's all done by electromagnetic interactions. This is Didcot Power Station in Oxfordshire. When operating at full capacity, Didcot generates around 2,000 megawatts of electricity. The heart of the power station is the turbine hall. 4 large alternators, each producing 500 megawatts. Despite their enormous size, the way they work is not too different from this, an alternator from a car. There are 2 main parts, a rotor, which turns in the middle, and a surrounding stationary part, the stator. The stator contains copper windings mounted on a soft iron ring. The stator is laminated, thus reducing the effects of eddy currents in this soft iron. The rotor also contains windings, called field windings, wrapped around a soft iron former. A DC current is passed through these windings so that they become an electromagnet. I can tell that soft iron is used for the former because it has not retained any noticeable magnetization after the current is removed. The alternator is used to convert the mechanical power of the rotating shaft into electrical power. The shaft turns the rotor, so we need a way of maintaining the DC supply to the rotor while it turns. This is achieved by means of these 2 copper slip rings and these 2 carbon brushes. The carbon brushes press against the copper slip rings so that as the rotor turns, a good electrical contact is maintained. So what does happen when the rotor turns? Here's a cross-section through an alternator. As the rotor turns, the lines of magnetic flux cut across the windings. The arrow indicates the direction of the magnetic field. You can see that the amount of flux cutting the windings varies. This variation can be plotted as a graph. If the stator windings are carefully designed, the flux crossing the windings varies sinusoidally. You should know from Faraday's law that the induced EMF across the stator windings is proportional to the rate of change of flux crossing the windings. The rate of change is the differential with respect to time. If the flux varies as a sine function, then its rate of change is a cosine function. So here is how the induced EMF varies with time. It too is a sinusoid. This is the output voltage from the alternator, an alternating voltage. So far I've only considered 1 set of stator windings. A real alternator has 3, each generating an independent sinusoidal voltage. The rotor will sweep past the other 2 sets at different times in the cycle. So the resulting EMFs will be out of phase with each other. As one cycle is 2 pi radians, or 360 degrees, the phase separation of the 3 EMFs is 2 pi over 3 radians, or 120 degrees. If a circuit is completed across any of these voltages, a current will flow. So we have a source of electrical power. But how do we take it to where it's needed? Sometimes cables are buried underground, but more often they're strung high above the countryside. Whenever you see overhead power lines, you'll always see the 3 separate phases that are produced by the alternators at the power station. These cables will have some resistance, and this is bad news for the efficiency of power transmission. Current flowing through a resistive load generates heat. The heat lost by these cables is given by the formula P little h equals I squared R, where I is the current, R the resistance, and P little h denotes the power lost as heat. So the electricity companies want to make R as small as possible to keep the heat losses low. The resistance R can be kept small by using a cable like this. It's made up of steel and aluminium. I can tell the steel from the aluminium with a magnet. The resistivity of aluminium is much lower than that of steel, so this is where the current flows. In order to keep the resistivity of the aluminium as low as possible, very pure aluminium is used. But using very pure aluminium gives it a low tensile strength, so that's why we need the steel here for structural support. What else can be done to minimize R? You'll recall that the resistance of a wire or cable is related to a material's property, resistivity, symbolized by the Greek letter rho, and to its length L and cross-sectional area A. One way is to reduce the length by taking the most direct route across the countryside from the power station to the communities that use the electricity. The power companies would want to do this anyway in order to keep down the capital costs of pylons and cables. It's not always possible, though, because of the shape of the national grid and the impact on the environment. The other factor we can tinker with is the cross-sectional area A. The resistance R is inversely proportional to A, so if we can make the area larger, we'll lower the resistance of the cable. But it's not as simple as that. If we clad the cable with extra aluminium, then we'll need extra steel for structural support. And that raises all sorts of issues, like the spacing of the pylon and the tension in the cable. So, the bigger the cable, the lower the heat loss, but at a price. Cable design, then, is as much to do with economics as it is with material science. I said earlier that the reason for trying to minimize R was to keep power losses in the cable low. If we can reduce I, then the saving will be very large indeed, because I is squared in this expression. Reducing the current can be done without adverse effect to the customer, since the aim is to transmit power regardless of current. Power is given by P equals IV, so if V is increased, then I can be reduced without affecting P. This is exactly what the power companies do. The backbone of the national grid is a so-called supergrid, where power is transmitted at a very high voltage, 400 kilovolts. At these voltages, the electrical breakdown of the air is a major problem, so the cables appear in groups of 4, thereby reducing the electric field at the surface of any one of them. But how do we get from 400 kV to this? Again, it's all made possible by electromagnetic interaction. The alternators in the power station generate around 23 kilovolts. Large transformers step up the voltage to 400 kV for distribution over the national grid, and smaller transformers near the consumer's end, like this pole-mounted one, step down the voltage to a more convenient 240 volts. In between the power station and the consumer, there may be a number of intermediate transformers located at substations, like this one at Claydon in Buckinghamshire. Inside this rather unassuming brick building, the 400 kilovolt supply is transformed, stepped down, to 132 kilovolts for more localized distribution. Although large, such transformers are identical in principle to this small one here. The bulk of the transformer comprises a soft iron core. Around the core a primary coil is wound, and on top of that one or more secondary coils are wound. A section through the transformer reveals the primary coil, it's the darker one, closest to the centre, and 3 secondary coils, 2 red and 1 more a copper colour. They're just discernible between the layers of insulation. Despite this difference in colour, they are in fact all made from copper. This is fairly usual because its resistivity is low and it's not prohibitively expensive. The core should have a high permeability, as we want the flux density to be as large as possible. To keep hysteresis losses to a minimum, we want a material with low remanence and coercivity, in other words, a soft magnetic material, soft iron. In fact, grain-oriented silicon iron is normally used. Apart from the materials involved, another important factor in transformer design is the number of turns in each winding. This transformer has 1500 turns in its primary winding. This gives the coil sufficient inductance to support 400 kV across its ends without drawing an excessive current. You should know that the turns ratio for a transformer is equal to the ratio of the voltages across the secondary and primary coils. If V in is 400 kV and V out is 132 kV, stop the tape and calculate the number of turns on the secondary coil. I'll give you the answer later. If you did that calculation, you'll know that the voltage across the primary coil is about 3 times that across the secondary coil, which is why there are larger insulators on the incoming side. The transformer gets hot, so there's a cooling system built alongside. If it gets hot, then there must be power losses. You should know from Unit 8 where the principal power losses are. Stop the tape and write them down. The core of both the big transformer and this one are laminated. The alternating magnetic flux in the core tries to induce alternating circular currents within the core. By laminating the core and separating the laminations with an insulating lacquer, the eddy currents are confined to individual laminations and their effect is minimized. Before we leave the substation, look at these porcelain insulators. Why are they made of porcelain? And why are they that shape? From the substation, the voltages get progressively smaller. Eventually terminating in the domestic supply. So here we are at the familiar 240 volt supply, about 100th of what it was at the alternator. And yet, as I said at the beginning, there is no direct electrical connection between the two. Now here's a summary of what we've covered, and you'll find the answers to my questions at the end of this section of the video. The alternator at the power station produced 3 power sources, separated in phase. Each phase is transmitted across the grid independently. Each one is stepped up at the power station for transmission across the grid. For more localized distribution, the voltage is stepped down so smaller pylons can be used. There is no direct connection between home and the power station. When a domestic appliance is switched on, a circuit is formed at the consumer's end of a transformer. This is separate from the circuit formed between the power station alternator and the step-up transformer, and the circuits formed between the transformers. These circuits are separate but not independent. They interact in transformers by the effects of electromagnetism. So, there's a lot to ponder when you switch off this tape and switch on the kettle.